This is the circuit diagram for our part 1 in lab 3. This is the 7-segment display. This is our freedom board, and this is the switches that we are using. For pin A on the 7-segment display, it is connected to PTC2 on the freedom board. Pin B on the 7-segment display is connected to PTC9 on the freedom board. Pin C is connected to PTC4. Pin D is connected to PTC7. Pin E is connected to PTC5. Pin F is connected to PTC8, and pin G is connected to PTC9. Both the middle pins of the top and bottom of the 7-segment display is connected to the VCC 3.3 volts from the freedom board, and one end of the switch is all connected to VCC to provide the supply, and then the other end of the switch from bottom up, the first switch from the bottom is connected to PTB0, the second switch from the bottom up is connected to PTC0, the third from the bottom up is PTE0, and finally the top one is connected to PTD0. And this is our block diagram. The freedom board will send the signal to the switch, and based on which switch is triggered, it will send the signal back to let the freedom board decide which portion of the LED on the 7-segment display to light up from the numbers 1 to 9 and 0. I think that one I can put the numbers on it. It's right. This is the table for how each switch turns on which number. For the number 1, switch 1 is turned on while the rest is turned off. For the number 2, switch 1 and 2 is turned on while the rest is turned off. The switch for number 3, switch 1, 2 and 3 is on while the last one is off. For switch 4, all 4 switches are turned on. For switch 5, switch number 1 is turned off while the rest is turned on. Switch number 6, switch 1 and 2 is turned off while switch 3 and 4 is on. For 7, 1, 2, 3 is off and the 4th one is on. For number 8, switch 1 and switch 4 is off while switch 2 and 3 is on. For number 9, 1 and 4 is on while 2 and 3 is off. For the number 0, all 4 switches are turned off.
This is our coding. First, we include the derivative.h, and we define that we got 7 segments for the 7-segment display, which is A to G. We define A to port C2, B to port C3, C to port C4, D to port C5, E to port C7, and F to port C8, G to port CG. Well, we got 4 switch 1 to port B0, switch 2 to port E0, switch 3 to port C0, and switch 4 to port B0. And here we create a function called delay for the to add the delay function. And after that, we create another function called initialize digit and set digit. This is the function we initialize all the port. At first, we enable the clock for port B, C, D, and E. And here we enable mux for port C, and we set it to high drive strength for all the port C, for 2, 3, 4, 5, 7, 8, 9. We set all to high drive strength. And for the switch, for port D, E, C, and B0, we set it to max 1, and we set it. First, we enable the pull and enable, and we set it to pull down. We set it to pull down for all the switch. This is the port direction. For GPIO-C, we set the direction of from A, B, C, D, E, and F, G. And for the switch, we make it inverted, which is pull down, active high. In the main function, at first we initialize the port, and then we set GPIO-C PSOR, which we disable all the output first to clear all the output. Then we create a for loop, which is infinite loop, to run the initialized digit. In initialized digit function, this is the switch. When we turn on the switch 1, it will show number 1. It sends number 1 to I, which will show number 1. And if switch 1 and 2 turn on together, it will show number 2. And switch 1, 2, 3 all together will show number 3. If all the switch is turned on, it will show number 4. And this one is only if switch 1 and 4 is on, it will show number 9. Else if only switch 2 and switch 3 is on, it will show number 8. Another else if this one, if switch 2, 3, 4 is on, it will show number 5. This one is if switch 3 and 4 is on, it will send 6 to I, which it will show number 6. For this one, if only switch 4 is on, it will show number 7. If every switch is turned off, it will show 0. In this function, set digit, which it will get the number from I, and then it set, if the number is 1, it will show number 1, and it will turn on the segment B and C, which will show number 1. This one is if the I is equal to 2, it will show number 2. If 3, then it will show number 3, and so on for all the number until 0.
This is our physical connection for the part 1 of the lab 3. If I flip switch 1, as you can see, number 1 appears on the 7-segment display. If I flip the second switch, number 2, 3, 4, 5, 6, 7. Switch come up. 8 and 9, and if I close all the switches, 0 will appear. Zero will appear if all the switches are off.
Okay.
Now you transfer the code for part 2.
Not this. Everything massive.
No, it's on.
Very good.
We are wrong. This one. So remove this one. Remove this one. don't have a connection for second part 2. I think you can directly use the board. This is the block diagram for the part 2 of lab 3. The light sensor detects the light in the surrounding area and sends a signal back to the Freedom board, where it will convert the analog signal, which is from the light sensor, to a digital signal. And based on the range that is set inside the Freedom board, it will display on the kitty what are the light levels as it's detecting. This is the light sensor should be on the top of the LED over here. So as for now, it's room brightness is showing around 900 plus on the kitty reading for this side. Then as if we bring in error reading from serial device.
Why they got disconnected?
This one recording.
Okay.
As you can see right now, the reading for the reading that we're getting from the board is around 900 plus. The lighting is room lighting. As we bring in the brighter source of light, you can see that it's slowly decreasing as the light source gets brighter and brighter, and it gets closer and closer. It will get to the point where it will decrease to a certain amount, and unless we provide a much brighter source of light, it will not go down any lower than that. Let's stop this one. I don't know what it affects. Hopefully it doesn't. This is our schematic for part 3 on lab 3. As the connection is the same as part 1, just that the switch has been removed. Everything else maintains the same, all the ports and connections from the 7 segment to the Freedom board. The block diagram shows that the light sensor detects the light in the surrounding area, sends an analog signal to be converted to a digital signal in the Freedom board, and based on the range that we set for each number, based on the brightness of the light, it will display on the 7-segment display to show how bright it is as the light sensor is detecting the light surrounding it. For now, this is the connection. For now, the switch is not being used. We are using the sensor at the top here. For now, it's showing 0, but as the light changes, there should be a change in you should see a change in the 7-segment display, slowly going up as the light is slowly brought closer and closer until the highest is number 9, and when we remove the light again, it slowly goes down all the way until 0. We didn't explain the
this is the code for part 3. At first, we include all the function, which is initialize digit, set digit, initialize ADC, and then the function to calibrate the ADC. This is the function for the do ADC conversion. This is the function delay function, and the port initialization. We add in the initialize for enable ADC clock. Others is all the same. This switch can be ignored. We don't use it anymore. We create a new integer, which is ADC data, outside of the main function. In the main function, at first we initialize. We add in the clock initialize. This is used for the display in the kitty, and we run port initialize and the initialize ADC. This initialize ADC is used to calibrate the port for the ADC, or the light sensor in here. ADC. We set the ADC mode to 0x02, which is the highest resolution mode, and all the others setting we set it all to 0 because we're not using it. We set the diff mask to 0 to disable the different. Sure. This is the code for calibrate the ADC. When it is success, then we will print out calibration successful. And in do ADC conversion, we change the channel to channel 19 as requested in the question. We change it to channel 19. Back to the main function. After that, we clear all the output, which we set PSOR and the 7 segment. We clear all the output first, then we run initialize digit. This is a function for initialize digit. We create an integer I, and then we get the ADC data which we create just now, same as the ADC conversion, which will get the light level, the value of light level. And we create if loop. If the ADC data, which is the light level, is less than 900 and it is more than 800, we will set a digit 1 in the 7 segment display. And if the value is between 800 and 700, we set it 2. When it is between 700 and 600 for the light level, we set digit 3. We set the integer I, same as 3, and then we send it to set digit, which will later display the number 3 in the 7 segment. and so on for all the light level. And the last one is when the light level is lower than 100, it will show number 9. When there is no light presence, it will show 0. This is a function for the set digit. When we get number 0, for example, in the initialized digit, which will send the number 0 to I, and then the I will be represented as the LED number. So if the LED number is 1, it will show number 1, which will set B and C to high, and it will show number 1. And all the other numbers are same. And after showing the number, we will clear the output again. So